All right, welcome, folks. Please give me your attention. You'll remember last class we talked about a mid-segment. And today we're going to talk more about things that are in the middle of triangles. Let's start with filling in some definitions. A mid-segment is a segment that joins the blanks of two sides of a triangle. We did mid-segments yesterday. It joins the two whats? Midpoints. Thank you. And let's draw that into a picture here for A, B. Let's make a point in the middle and put in the congruence marks to show that it's exactly in the middle. And then when we connect it, we create a segment connecting midpoints called a mid-segment. Bless you. Next one is a perpendicular bisector. We're going to create a perpendicular bisector to a side. And what that is a line segment array that divides the segment into two blank parts and is blank to the segment. Close. Equal or congruent, and is what to the segment that it intersects? Good. Perpendicular, because it says perpendicular. A bisector means it splits it in half. The perpendicular means it meets in a right angle. And what that would look like in this picture is you'd first find the midpoint, and then you'd take a straight edge and draw a nice straight line going up. And that line will be perpendicular to AC. Now, in this case, did my perpendicular bisector go through the vertex point B? It didn't. Will it sometimes? Yeah, sure, it could. If it's an isosceles triangle, it would, but not all the time. Next, we'll look at an angle bisector. It's a segment array that divides an angle into what? Two what kind of parts? Good, equal or congruent parts. So it'll be coming out of B in such a way that it splits this angle into two equal parts. Does that necessarily go through the midpoint of AC? No, it could, doesn't have to. Is it perpendicular to AC? No, could be, doesn't have to be. Does it definitely go through B? Yes. All these are components about these that we have to keep track of. I'll give you some tools to manage them in a little bit. A median, we talked about this one as well. It's a segment that connects a blank of a triangle to the blank of the opposite side. Remember a median? Good, to the midpoint of the opposite side, and we're coming from the what? What do you call the top point of a triangle? Nice, vertex. So I'd find wherever the midpoint is of this side, and then I'd take my straight edge and connect B to that point. That's a median. And the last one of our special segments is an altitude. What do you think of when you hear the word altitude? Height. Height, good. So if you're at point B on a mountain and you want to figure out your height, would you measure how long this side is? Or how long this side is? No, you'd want to like drop a string with a rock on it, wouldn't you? You want to find out exactly how far it is from this point straight down, so perpendicular to the base. So what's the difference between a perpendicular bisector and an altitude?
Altitude makes it
altitude what? Good. The perpendicular bisector has to go through the midpoint. The altitude doesn't. The altitude goes through the vertex. The perpendicular bisector doesn't. Now, what's this all leading towards? Let's have a discussion for a second about what the center means, or middle. If I draw a circle, what is the center point of a circle? Okay, but what does that mean?
Like the point where it's equal distance away.
You're exactly right. Really good. It's the point that is the equal distance from every single point on the circle. We agree?
Yeah.
Okay, that's the center. But what if I take that shape and change it? What if it's no longer a circle? Can we agree that this is not the center of this square? Everyone knows what it looks like, but how do you define the center? How could you tell somebody what the center is?
In the middle of all angles.
In the middle of all angles. Do you mean it's the same distance from all the angles?
Yeah.
Would you guys agree that that's a valid definition? Like a circle was all points, but now we're going to have to go, that should go to that corner, to the angles. Is that the only way we could define it? Good. Couldn't it also be the same distance from the sides? As measured perpendicularly, because that's the shortest distance. Okay. What about an equilateral triangle? How would you describe where the center is? Somebody whispered it. Can I use the same definitions?
Yeah.
Yeah. It's the point that's equidistant from all three vertices, or is equidistant from all three sides. We okay with that? Now, interestingly, because there are other types of triangles, depending upon the triangle we're looking at, things are different. Like, would you agree that my center to the angles is about there? That's about the same distance to all three angles. But if I was looking for the distance from the sides, that'd be more like down there. So in fact, there's two different centers in this triangle. And in fact, let me blow your mind a little bit. Is this a triangle? Okay. Can we agree that one of our centers is the point that is about here? In other words, the same distance here as here as here. Does that look about right? But the other center is supposed to be a point that is equidistant from all three vertices. And up here, we said this was the point that was equidistant from all three vertices, right? One way I could validate that, and of course I was estimating that, is that I could put my compass on that center, the needle on the center, and measure the length to one vertex and make a circle, and it should go through all three vertices, shouldn't it? That would describe that it's the same distance from all three. So where would my center have to be so that it's the same distance from all three vertices here?
Is it like outside the triangle?
It's outside the triangle, isn't it? Not even there, but somewhere down around here. How weird is that, that the center of this triangle is outside the triangle? And then there's another concept as well. In fact, in all, there are 4 different centers of triangles we're going to work with today. And in order to do that, we're going to use our construction tools. So first, let's finish off our altitude. A segment that connects a vertex of a triangle to the opposite side so that it is perpendicular to that side. Everybody, please take your sheet of white paper and hold it in forks like we often do. And do you remember the pro tip? How do we do construction so that the needle doesn't slide around our table? Get a book or a stack of papers or something underneath it. So please, if you want to go get the geometry book and put it underneath your needle, that's fine. Okay, would you please turn your paper landscape Okay, turn your paper landscape with your 4 folds. In the top left corner, I want you to write perpendicular bisector. And then draw yourself a triangle. I want you to use a straight edge. I want you to be very precise with it. And do not make it an equilateral triangle. You can make it right or acute or obtuse. Many choices. Just don't make all 3 sides the same length. We've done perpendicular bisectors before. Do you remember the process? I'm going to take my compass. I'm going to put the needle on one of my vertices, bottom right. And how open should I make my compass? About there? More than half. As long as it goes more than halfway, I'm good. And I'm going to make myself an arc. And then I'll pick up the compass and move it to the other side, this other angle. Anchor it carefully and use the same length to make another corresponding arc.
What do we do?
We're going from our vertex here, and we're making an arc that is more than halfway, and then flipping our compass over and doing the same from the other side. And that gives us this football. If I look at the endpoints of this football as points of intersection, I'm going to connect them using my straight edge. And be very, very precise with this, please. You want to go right through that point of intersection. You don't want to miss it. By doing that, I end up with a perpendicular line that bisects. Okay, I'm going to circulate around. Everybody, please make sure that you are able to do this, and make sure your neighbor's able to do this as well.
I can get it on this one. Yeah. Yeah. Well, and you could have fixed that by going when you go more than halfway, a little less than more than halfway, right? Just a little bit less than so much over that.
All right. As I walk around, I see lots of really good perpendicular bisectors. You guys ready for the magic move? Pay very careful attention. Everyone watch the screen. This is a really technical maneuver. Ready? Everyone watching? Oh, look at that. Oh, wait a minute. No way. Yeah. Okay, now I want to do the same thing from this side. Make a perpendicular bisector from this side. So I'm going to needle on the corner, go more than halfway. And then connect the endpoints of that football. Again, be as precise as you can with it. Mark it as perpendicular and bisector. It is exactly the same thing we just did. And what do you notice about these two perpendicular bisectors? Do they meet? Do they intersect? Yes. Is that meaningful? I mean, two lines either meet or they're parallel. These two lines were never going to be parallel. So that doesn't seem that interesting. But now, do another magic move. I want you to construct the third perpendicular bisector. And pay attention to where your marks are, because it's going to get a little crowded in here. Again, pay attention to which arc you're talking about, because it's going to get a little crowded in here. What do you notice? They all meet at one point. That's kind of crazy. Yeah. Then you weren't as precise as you needed to be. Okay, hold on. I'm going to come look at yours. Here. All right, I see a lot of good ones. Remember how in algebra, when you solve a problem, you can check it by plugging it back in. You know if you're right or wrong. This particular one, we can also know if we're right or wrong. Please be quiet. Here's the way. Everybody put your needle at your point of intersection and adjust your compass so that it goes just to one of the corners, one vertex. And then draw a circle with that radius. And if you did it correctly, what's going to happen?
It's going to touch all four.
It's going to touch all three vertices.
So Mr. Vernon. Yeah. Okay. So okay, so your precision is pretty good, but not perfect, which is okay. This is a hand-done progress.
All right. Let's note this so that it looks like something with information on it. We've taken three perpendicular bisectors And as a result, those three bisectors met at a point of intersection called the circumcenter. This is the first of our triangle centers. And it is that point right there in the middle. The circumcenter is one of our four middles, one of our four centers of the triangle, and it has some special features to it. So come back to our notes, please. You'll notice just below altitude, it says the circumcenter, that point at which three blanks intersect a triangle. What did we produce to make the circumcenter? Good, perpendicular bisectors. Now, look at the picture they've given us to the right. This is supposed to model a circumcenter, but these are super confusing. Can you list for me or state for me a perpendicular bisector in that triangle? XM, you guys agree? How do we know? Well, these marks mean that it's a bisector and it's got a perpendicular. I think you're exactly right. Is that the same line as XC? No, that's bent, isn't it? So that's something else. What does MC have to do with anything? Like we've got three perpendicular bisectors. I can see them, MZ, XM, and MY. MC is the distance to the vertex. And we said that the three distances to the vertex with the circumcenter are what? Aren't they all the same? In other words, if I were to put my needle here at the circumcenter and I'd set my radius to be the length of AM, wouldn't that be the same as MB and the same as MC? So what I need you to think about here is an if-then statement. If you draw three perpendicular bisectors, then equidistant from vertices. And really, it's a logic chain. If you draw three perpendicular bisectors, then you produce a circumcenter. If you produce a circumcenter, then it's equidistant from all three vertices. All right, next one's going to be an incenter. It's a different type of center. The point at which three, what would you say from the picture we're producing here? Very good. Angle bisectors. And let's see what that does. Let's go back to our constructions. And I'm going to choose the upper right one here. I'm going to draw myself another triangle. Three angle bisectors. And be as precise as you can in drawing your triangle. Make sure that your vertices all hit at the same points. Make it clear where those points are so you can put a needle there. You don't make a good, clean triangle, it won't work. Angle bisectors. You guys remember how to do angle bisectors? We did these before. It's been a little while, though. Say again? Triangle centers. 34. All right, I'm going to put my needle on one vertex, and I'm going to open my compass to be, I don't know, about halfway maybe, and make an arc. This is called a reference arc. It doesn't matter what side length you choose. Having done that, I've now produced intersections along two sides of the triangle. And I'm going to turn my page as if these are endpoints of a segment, and I'm going to do a perpendicular bisector between them. So from this point of intersection, I'm going to go more than halfway and make a little arc. And I'll use that same length from the other point of intersection. Make a second arc. The reference arc can be any size. And now you go from both of these 2 points more than halfway to the other one. And when I connect these 2 endpoints of the football, it should go through the vertex of my triangle. And remember back in Unit 1, 3 points are always, sometimes, or never collinear. Sometimes. Always. No, not always. 2 points are always collinear. For 3 points to be collinear, this is like a check to see if I did it correctly. If all 3 points line up, I did it correctly. If they don't line up, check your work. See, maybe you didn't do it correctly.
So you have a arc, right? So you make the original, and then 2 points that are highlighted, you make another football on that. Yeah, so place one top of the arc, and then
as we did before, do it again. Turn your triangle and do it again. Yep. I just did the exact same thing we did over on this angle to this angle. And now I'm going to do it to the third angle. I'm going to make a reference arc. And then from each of the points of intersection here, I go more than halfway. Remember how last time when we had the perpendicular bisectors forming the circumcenter, we were able to verify that we did a pretty good job by making a circle through the outer vertices. Can you guys be quiet, please? So how do I know if I've done it correctly here? This is the angle bisectors, and it produces something called the incenter. It's different than the circumcenter. And in fact, it's not going to have the same features. So if I go from this point and I look at how long it is to this vertex, that's going to be a different value than this other one. See how I'm shorter here and I'm shorter here? Because an incenter is not supposed to be the same distance from all 3 vertices, but what an incenter is the same distance from all 3 sides. So the incenter is a center that allows you to draw a circle that fits inside the triangle. So test that. See if you can fit it in. And this is always a bit of a adjustment, right? Because I missed it here a little bit. It's not very precise. Let's go back to our notes. We said that it's the 3 angle bisectors meeting. So in other words, these are the angle bisectors. Those are forming it. Those are the if angle bisectors. Then what's the conclusion to this? What's the result of doing this? Then I should be able to draw a circle along the inside of this thing, because the radius of the three sides would all be the same. Then equidistant from sides. All right, the third one is the point at which three, what are these? Well, a mid-segment is a connection of a midpoint to a midpoint. So that would be across here. Altitude is perpendicular to the base. Medians, good. From the midpoints to the opposite vertex. From the midpoint to the opposite vertex. These are all medians. And if you have medians together, they all form a centroid. And if you have a centroid, it's the balancing point. In other words, have you ever seen people who can like spin things on their fingers, like frisbees or balls or chairs or like crazy things? The only way you can do that is by finding the center of gravity, a way that it balances. And so if I was trying to put my finger in the middle of this triangle so it would stick on top of my finger and perfectly balance, that's the centroid. That's the one we just found. It won't make a circle on the inside. It won't make a circle on the outside. It's just the balancing point. So let's choose another one of our boxes here. We're only going to make 3 boxes today, so you got plenty of room. This third one is going to be medians. What is a median? It's not a small, it's not a large. It connects a vertex to the midpoint of the opposite side. So to draw that median, I just need to know the midpoint of this side. Do we have any tools to find the midpoint of a side? What tool is it? It's the perpendicular bisector. We're just not going to draw the whole perpendicular part. We're just going to go more than halfway. And then the same from the other corner, more than halfway. I make my little football. But instead of drawing the whole perpendicular bisector going all the way up, all I need is the little part that shows that it's in the middle. And then I'll connect that to the opposite vertex. And let's do that to all 3 sides. So just find the midpoint by going more than halfway. Ooh, I made that a little tight. I'm going to do that again. That's just too tight. By the way, pro tip, do you notice how I'm able to erase my mistakes and it doesn't erase the triangle? Why is that? I use pen for the triangle itself because that's easy. And then I use pencil for the constructions because those maybe sometimes need to be redone. Just looking for that midpoint. Okay, so that gave us the three medians meeting at a single center. This center is called the centroid. And this is the center of gravity. It also has some other features to it. Now, the orthocenter is the last one. Any guesses what the special segments are that form an orthocenter? Altitude. Very good. Process of elimination, it's the altitudes. We're not going to actually construct that today. We'll save that for next class. But flip this notes page over. Would you agree that we've covered a lot of content already today? It's a bunch of facts. And I got to get you somehow synthesizing this information, pulling it together and seeing what matches. Please be quiet. This is when you do the synthesis of the information. This is the hardest part. So I need your attention. We're going to organize our data to help us see some patterns. If we take a perpendicular bisector, does it go through the vertex? And let's draw ourselves a non-equilateral triangle, just a little sketch, and remind ourselves what a perpendicular bisector looks like. Everyone draw that sketch. Does this go through the vertex of the triangle? No. No, so leave the spot blank. Does it definitely go through the midpoint of a side? Yeah. Yes, so write a yes in there. Is it perpendicular? Yes. Is it an angle bisector? No. And when I do the three perpendicular bisectors, what center does it form? The circumcenter. And the circumcenter has what special features? Equidistant from vertices. And another way of seeing that same fact is it's the center of a circle that circumscribes the triangle. Do you know the word circumscribe? Anyone know what circum means? Around, very good. And scribe? To write or draw, very good. So it's to draw around the outside. Okay, let's draw ourselves a little angle bisector. And again, if we make it a non-equilateral triangle, it's more meaningful. Okay, what about the second one, angle bisector? Does it always go through the vertex? Yes. Does it always go through the midpoint of a side? No. Is it always perpendicular? No. Is it always an angle bisector? Yeah. Oops, that's the wrong one. This one. And what center is formed by the angle bisectors? Very good. Incenter. And what's special about the incenter? Equidistant from sides. And it's the center of a circle that is inscribed, drawn inside the triangle. All right, let's draw ourselves a median. Do you remember what a median is? Good, midpoint to the vertex. So does it definitely go through the vertex? Yes. Does it go through the midpoint of a side? Yes. Is it perpendicular? No. Is it an angle bisector? No. What center is formed by the medians? Centroid. And this has actually two features. One we've already talked about. It's the center of balance. The second one we haven't talked about yet. It splits the medians in a 1:2 ratio. We'll talk more about that in just a second. All right, let's do the last one, altitude. Again, think about how you would draw that one. Altitude would go straight down and perpendicular, right? Is it going to go through the vertex? Yes. Is it going through the midpoint of the side? No. Is it perpendicular? Yes. Is it an angle bisector? No. And the center name? Orthocenter. And sadly, the special feature of this is, for our purposes, nada, nothing, niente. How do you say nothing in French? Anyone know? I don't know. I'm going to France in the spring. I need to learn this stuff. Okay, why did we do this? Well, please note, there's now how many features for each of these centers? 2. which means if we look at a picture and we see that, I don't know, it goes through the midpoint of the side, that tells me immediately that that's got to be what? Either a perpendicular bisector forming a circumcenter or a median forming a centroid. This is what your homework for tonight is going to be. What you've just done is the notes. Could you guys stop talking, please? What you've just done is the notes. The notes are not to be turned in on Canvas. But that page that we just did, the two-sided page, is super helpful to you being successful with the homework. All right, let's go through these because I think these are difficult, and that's why I've put so much time into organizing it. The blank blank of the sides of a triangle intersect at a point called the circumcenter. Sure, if you need to. What things make the circumcenter?
No, perpendicular bisectors.
Perpendicular bisectors. Thank you. And the circumcenter is always equidistant from the blanks of the triangle. Vertices. List the perpendicular bisectors. Look at this picture. You said X, P, and E?
Oh, no, F, D, and E.
F, D, and E. Well, those are all midpoints, which is helpful because bisectors go through the midpoints. But we need something that goes through the midpoint and is perpendicular. Points can't be perpendicular, so it's got to be a segment. So like PF. What's another one?
PE.
Good. PE. Another one? PD. Name the circumcenter. P. Now, it says list all congruent segments. It gave us 3 sets of congruent segments, but that's not really what is important here. Remember, I described that we want to think about the if-then. If we draw 3 perpendicular bisectors, then we produce a circumcenter. If we have a circumcenter, then it's equidistant from all 3 vertices. So the conclusion in the end is that it's equidistant from all 3 vertices. That means when you look at this picture, you should be able to come up with 3 segments that are congruent to each other based on the fact that this is a circumcenter. What are those 3 segments?
PC, PB, PF.
You guys see that? This is the distance from the center to a vertex. And what we're saying is that it's equidistant from the center to all 3 vertices. So PC, comma, PB, comma, PA. Those should all be equal. Now, what I find so hard about this particular part of the unit is interpreting the pictures because they're kind of complicated. So first of all, we're trying to find that we're told that this is a circumcenter. Okay, that gives us information. That means X is what point? It's right in the middle, isn't it? So if XU is 19, how long is TX? Also 19, which means how long is TU? Yeah, 19 times 2 equals 38. Now, VY, if we know this whole length is 34 and Y is a midpoint, then VY is how big? 34 over 2 is 17. All right, those parts are easy. What about UZ? Good. Why? Because they're all equidistant vertices from that center. So if this is 21, so is that. Now, here's where it gets awkward. What about WV?
36.
Nope.
Oh.
Nope. I'm going to draw this part of the triangle out. We know that this part is 15. We know this part is 21. And we're looking for this part.
Just add 2 to 1 ratio or something.
Ooh, that's in the medians and the centroid. A squared plus B squared equals C squared. That's a great idea if this is a right triangle, is it? Yeah, because circumcenter means these are perpendicular bisectors. So yes, that is a right angle. So now I can say 15 squared plus question mark squared equals 21 squared. 225 plus question mark squared equals 441. Question mark squared equals 216. So question mark equals square root of 216. And I'm okay just leaving it like that for now. We could do a decimal approximation. We could simplify the radicals, all kinds of things. What about TV? If we just found that this part is square root of 216, how long is the whole length? Good. 2 times the square root of 216. Is that a simplified form? No, not at all. But that's okay for now. That's what we can do without a calculator. Please move on to the incenter. The blank blank of the angles of a triangle intersect at a point called the incenter. What parts form the incenter? Good. Angle bisectors. And the incenter is always equidistant from the blank of the triangle. And if you're not sure about this, you should be looking here, right? Angle bisector equidistant from the sides. So list the angle bisectors. What's one of them? Say again, please. DP or BP? Angle bisector, splitting the angle in half. So BP would be one. PC would be another. AP would be another. Incenter is P. Now list all congruent segments. Again, think about the conclusion of this. If you take 3 angle bisectors, then they make an incenter. If you have an incenter, then it's equidistant to the sides. So what new congruent segments could we strike here?
DP.
Good. DP, comma, EP, comma, FP. If this is the incenter, those pieces will be the same. So NP is congruent to what? Or equal to how much? 8, right? Because if this is an incenter, then all those distances to the sides are the same. What about NK?
I think it's 17.
You're right, but why?
So you know that like NP is equal to NP, right?
This piece is the same as OP, yep.
Right. So,
and then this is reflexive, isn't it?
Yeah.
So these two triangles are what? Congruent by RHL,
yeah,
which means corresponding parts are also congruent. And this is only true in an incenter, that these two parts will be the same. Whatever these are, these will be the same. This 35 will be the same as over there. Okay. How would you find PK? Yep, a squared plus b squared equals c squared. We don't know what this is. We know this side is 17. We know this side is 8. We can do the Pythagorean theorem to find that. Okay. Please go to the second page. The median is a segment joining what and what? Vertex to the midpoint. The three medians make the centroid. So let's list the medians. Give me one of the medians. DC sounds good. Give me another one. Someone different? EA sounds good. Someone new, give me the last one. BF, good. And again, they're giving us P as the centroid. Now, what special properties exist for the median? This is the new one that I haven't told you about yet. If we create a centroid, it splits the median in exactly a 1-to-2 ratio, which means that BP over PF is equal to what ratio? Two to 1. In other words, if this piece were 10, how long would this piece have to be? 5. What if I said DP is to DC? If this centroid splits this into 1-to-2 ratio, I'm saying DP to the whole length. What's that ratio? 1-to-3. Well, if this part is X and this part is 2X, when I'm comparing DP, there's 1X, to DC, which is 1X plus 2X or 3X, that ratio is 1-to-3. What if I said AE to AP? Almost. Nope. Almost. 3-to-2. Right? AE is all three parts, and I'm putting it over AP, which is two of those parts. Okay, so let's look at number 1 here to see if we can apply this. If we know that I'll find each measure, KM. Okay, these are medians, right? Centroids are medians. So if you know that JK is 22, how long is KM? 11, because it's going to be half as much. This whole thing is about that, just the medians. But over here, it gets more interesting. If TZ is 60, how long is ZY? Good, 30. And if XZ is 28, how long is XV? Well, this part is 56. So ZV would be 56. How long is XV? 84. Okay, I think you've got what you need. This page is going, well, let me do one more of these. Flip to the last page. What's this? Is this the circumcenter, the incenter, the centroid, or the orthocenter?
That's the midpoint. The incenter.
That's the incenter?
I think so.
Okay, so remember this chart? This is why we've got this chart. What do you see? What features are shown here?
Oh, no, that was I thought it was going to that.
What features are shown here? Right angles, perpendicular. So we know we're either dealing with the perpendicular bisectors or the altitudes. So the difference is, does it go through the midpoint of the side and does it go through the vertex? It goes through the vertex in all three cases. So therefore, these lines are what kinds of special segments? Altitudes, which means this center is which center? Orthocenter. All right, what about this number 10? I think this one's particularly hard. Look at your chart and see if you can figure out which features it's got. Don't say it out loud yet. Just 1 second. Just 1 second. Okay, folks, because you see midpoints and you see perpendicular, what kinds of segments are these? These are perpendicular bisectors, which makes this a circumcenter. Okay, please finish up these 3 pages as your homework. Submit them in Canvas. You do not need to submit the notes in Canvas. You've got about 5 minutes left.